I have the distinct pleasure to introduce one of our staff engineers from SRS, Francisco. Chico. Here you go.
Thank you. Thanks for coming to my talk. So yeah, so I'm a staff engineer in SRS, working with the company since 2018. And yeah, I did contributions both to the 4G and 5G code bases. And so these are my technical interests in the company. So I work a lot with the Max scheduler, with our L2, L3 system architecture, parallelization of our code and concurrency management, and I'm a modern C++ advocate. So I'm responsible for modernizing some of our code. So if you like C, I'm your enemy, I'm sorry. And yeah, so who is this for? This talk is generally for people to better understand our architecture, our stack, learn a bit more about its features and capabilities, feel a bit more confident at navigating our code, and more effectively deploy our networks based on srsRAN. I'll assume that during the talk you'll have you know what. I'll assume that you know some basic concepts about NR and ORAN, like I don't have to explain what a distributed unit is and so on. And this talk is also for people with a beginner to intermediate level of familiarity with our code. So, but before I jump into the DU high architecture, I just wanted to make sure everyone here understands the type of environment we work in. So what are the requirements and constraints that usually we face and how they shape the design of our product. So the first requirement that I'm going to talk about is the latency requirements. As you may know, the DU is a real-time system. And what that usually means is that operations have a deadline to complete. And if they don't complete in that deadline, there is a timeout, and the result of the computation is discarded. And the part of being discarded, okay, it contributes for a wastage of computational resources, but the bad part about timeouts in terms of RAN communications is that the users will feel a drop in quality of service, dropped throughput, increased latency, and so on. So we always have to think about algorithms from in terms of their upper bound latencies, at least in the lower layers of the DU. And so we really work a lot on trying to avoid operations with unbounded latency, like mutexes and so on. And that's what I usually care more about when I'm designing the architectures. And with NR, there were some introductions, some complications being introduced. Now we have higher numerologies, which means shorter TTIs. And we have these services that focus mostly on the latency, like ultra-reliable low latency. Another requirement is throughput and scalability. With NR, everything got more demanding. So now we have to support 100 megahertz cells. We have to support. We also want to support more than the number of users that we supported in SRS LTE. Last tests I've done, we were supporting more than 800 users per cell. More advanced antenna schemes and more cells per machine, up to 16. Robustness is another constraint, requirement. Our code needs to run for days without crashes or degradation. And this puts some requirements on our testing facilities with all sorts of tests, like unit tests to sanitizers to end-to-end tests, and so on. And the last one, but not least, is the flexibility, malleability. Okay, it's a bit cut. But so as you may know, SRS, we don't provide black box solutions, black box fully integrated solutions. Our code has to be very malleable for the end goals of our users, because we cannot make any assumptions on how you guys, what splits you guys are going to use, what machine you're going to run our code, what type of interoperability you need with the third-party vendors. We cannot make assumptions, many assumptions regarding that. So our code, and this is the part that that I think we bring a huge benefit to the community, is the malleability and flexibility of our code. So now moving on to the architecture of the DU-High. So, but before that, let me just explain what a DU-High is. The DU can be divided into two parts: DU-Low for layer 1 operations and DU-High for layer 2, so MAC and RLC. The DU-High communicates with the DU-Low through the FAPI interface, which is split 6, and it communicates with the CUCP and CUP through the F1 interfaces. It can communicate with more than one CUP, and the DU-High communicates with the RIC and the SMO through the E2 and the O1. And here I showed the components, the main components of our stack. Some of them are probably familiar to you, like MAC, Scheduler, RLC. But there is one here that for people that are not familiarized with our codes might raise some eyebrows. That component is the DU manager. So what is it for? Like usually you don't see it in diagrams online, component called like this. So we introduced the DU manager in our architecture because we felt that we needed a centralized point of control and the decision making for the DU. So, and it will decide things like configurations for the users, when to activate and deactivate cells, and so on. And we call these operations, these control plane tasks that are internal to the DU, we call it DU procedures. And usually the way it works is the DU manager receives events and requests from other components of the DU, so other layers, and those events could be radio link failures being detected in the lower layers. It could be requests from the CUCP to the DU via F1 app to change a UE configuration. Could be all sorts of events. You'll gather those events, process them, and makes the decisions, and the decisions will be translated into commands that are sent to the remaining layers of the DU. Commands like updating the bearers of a user, removing or adding new users, and so on. And then, if I had to pick the most important component of the DU manager, is the UE manager. And its function is to schedule and process UE procedures, UE specific procedures. And the way but it does this with some rules. UEs, the procedures of UEs, for a single UE have to run in sequence. We don't want concurrency of procedures for a single UE. We don't want, because that could lead to lead to chaos. We could have, imagine if we had procedure coming from the CUCP to the DU to remove a user, while the E2 is trying to configure that same user at the same time. That conflict would be very hard to solve if we didn't ensure that procedures always run in sequence. So they start, they complete, and only after they complete, another procedure can run. So we ensure that this rule, but if we did this for all users, our stack would be very slow, very unresponsive. So we have to have concurrency across users. So even if they might be running the same thread, we have to ensure that the procedures of different users don't block each other and can run in a concurrent manner. And we do this through these task schedulers. Here, I mentioned the name of the class in our code base, the FIFO async task scheduler, and each user has a different scheduler. These tasks are what are coroutines. We use coroutines a lot in our code, because they are a clean way to ensure these ensure concurrency across users, even if they are running the same thread, but still ensure that the tasks of each user run in sequence. Now we have the F1 app, which is, I would say, not too interesting in terms of architecture. It usually communicates with the DU manager and with the RLC. The RLC to send the RRC containers to the lower layer to be sent over the air. Those RRC containers can be RRC reconfigurations, setups, and so on that need to be sent to the user. And then it communicates with the DU manager to pass to the DU manager requests from the CUCP regarding the state of users, about our cells, and so on. And usually it flows a bit like this, like most procedures of the F1 app have a bit of a structure similar to this that you see on the right. Then there is also the NRU. I would say not super interesting, so I'll skip it. There is the E2 agent, which you should see just in stock, like now was yesterday, so you have to see it online if you miss it. Moving on, so the RLC layer. So I'm not a specialist of the RLC layer, but so I'm not going to dive too in depth in it. But one thing I would like to point out that is a difference between the srsLTE and the NR and our new stack is that so in srsLTE we had RLC as one big class that contain a repository of UEs and logical channels, and every time a PDU or a SDU would enter the RLC class, we would have to do that lookup of who is this PDU for, find the bearer, and pass the bearer to that the PDU to that bearer. We scratched that design and followed more an approach of direct connection of. So the RLC is now just there is no big class, a big RLC class. It's only individual RLC entities, which are RLC bearers, and they connect directly to the lower and upper layers. So whenever a PDU arrives, for instance, to the MAC from the PHY, and there is this demultiplexing based on logical channel ID, we reach the MAC logical channel, and then the MAC logical channel passes it directly to RLC entity, and the RLC passes the PDU directly to the F1 app on NRU, which is passed to the CU. So this direct connection between bearers is maintained by the DU manager. Again, the DU manager, the big brain on our DU stack. And yeah, so that's, I think, an important aspect. And the fact, when we did it this way, this allowed us to more easily parallelize our like tasks across bearers. Then we have the scheduler. So these are currently some of our supported features in the scheduler. The scheduler in the NR supports many TDD patterns. I mean, we tried many. So far, didn't see any big limitation. So it's very flexible on that regard. MIMO supports different types of PUCCH, F0, F1, and F2, different DCI formats, multiple cells, more than 800 users. Now multiple scheduling policies, proportional fair, round robin. You can add more if you want. We now have run slicing, that's a new addition, and the outer link loop link adaptation. So just to give a brief description of how the MAC scheduler works, it performs real-time decisions about spectrum resource usage, both for downlink and uplink. On every TTI, it receives all the events coming from the outside world. Those events can be feedback about the connection coming from the PHY, could be UE configuration updates coming from the DU manager, could be RLC occupancy updates coming from the RLC. It processes those events and comes up with a decision for the downlink and uplink resource grid utilization. And that grid utilization is basically a list of grants that the scheduler, passes to the lower layers. Then maybe the most important component of our scheduler is a resource grid, and which is basically keeps track of the resource usage in the spectrum, and he has to work with many slots at the same time. So on each slot indication that the scheduler receives, he may have to alter multiple slots at once. Like here, I give the example of for a downlink grant allocation. We have to change the resource grid in 3 different slots. In the first slot for allocating the PDCCH, if the case 0 is 1, we have to allocate in the next slot the PDSCH grant. And if the K1 is 2, we have to allocate the PUCCH 2 slots ahead. So it has this, it performs this task. And for grants that have higher priority, like SSBs and SIBs and so on, we want to ensure that they always have space to be allocated. They are not, like, we don't want user allocations to take all the resources and not leave anything for SSBs or SIBs, because SSBs and SIBs have higher priority. So what we do to ensure this prioritization is that we allocate usually these more important allocations ahead in time. So for instance, I could allocate here the SSB at slot 4 when I'm receiving the slot indication at slot 0, and when it reaches the turn of allocating in the slot 4, the SSB is already there. No one is going to take that grant away for other purposes. So these are, I mean, the schedule is quite vast, but I try to here kind of explain more or less how it usually works. So we have the resource grid that I was talking on the right side. We have many schedulers for different types of signaling, SSB, CSI, SIBs, and so on. They update the resource grid, and then the signaling schedulers are a bit simpler, but then we have the UE-specific scheduling that has to go through a longer chain of events. So we have configuration, channel feedback reaching the UE event manager. The event manager enqueues those events to be processed asynchronously, so we don't have for more efficient processing and avoid some multiplexing for too long. Then the event manager, when a slot indication arrives, will pick those events, process them asynchronously, and pass them on to different components. One of them is the UE repository that contains the context of the UEs in the scheduler. But we also have to update other components like the UE scheduler to alter the scheduling policy and so on. And if you want to change the type of scheduling policy, like from proportional fair and to round robin, for instance, you don't have to really change anything else except for the scheduling policy class, so we try to abstract all the complications of scheduling away from you guys, so that if you need to play with the policy, the scheduling policy, you only change the scheduling policy implementation for another, and everything else remains the same. So, and this is here I just wanted to show that the code kind of maps well to what I was describing of calling the different schedulers and like in sequence, and updating the resource grid. I pass the resource grid as a parameter to be updated. Then we have run slicing, as I was saying. That's a new addition. You can configure, so each run slice contains a SST and SD associated to it. It has a dedicated scheduling policy, round robin proportional fair, and the minimum and maximum PRB ratio that defines how many resources that slice can use. And the UE data radio bearers can be mapped independently to slices. And here is just an example of how we configure slices in our application configuration file. It's just very simple. You have a list of slices, as I was mentioning, and the different parameters that you can define for each one of them. There was an issue with the indentation for, don't know what happened, but okay. So we also have outer loop link adaptation, which is this mechanism to adapt the MCS based on experience blur. Yep, and it's quite, right now it's a simple algorithm. You guys can play with it and try to improve it. Let me know when if you have positive results. And then, okay, for the Mac, we have, so the Mac is responsible for enqueuing the queuing PDUs. And this is our architecture for the Mac layer. So we have this separation to 4 main components for the Mac. Okay, one of them is a scheduler that I just described. That is technically part of the Mac. But I wanted to explain what the other components do. So you have the Mac uplink that just receives PDUs coming from the from the PHY, decodes them and tries to pass them on to the RLC as SDUs. You have the Mac downlink that has this close communication with the scheduler to ask the scheduler to make decisions, and then based on the result of the scheduler, it then has to interact with the RLC to ask for the data and pass then that data and the grants from the scheduler back to the FAPI. And we keep the uplink and downlink completely decoupled from each other. This gives us extra control in the allocation of threads to these components. Then the Mac controller is the component that interfaces with the DU manager, receives configurations from the DU manager, and then picks those configurations and tries to apply the changes on the Mac uplink and Mac downlink and in the scheduler in a very coordinated fashion, so there are no problems with the concurrencies. So, and our code matches quite well that figure I just showed. So we have, as you can see, we have Mac scheduler, downlink unit, uplink unit, and control. And the file structure also matches the figure. Then we have the FAPI as the last component I wanted to mention. That basically the FAPI high is implements the DU high side of the FAPI protocol. It decodes indications coming from the FAPI low on the DU low side. Those indications can be feedback and errors and so on. And then passes back to the FAPI low the decisions made by the Mac and the scheduler. So these three are the 3 main messages: downlink TTI requests with the signaling, and the TX data request with the Mac PDUs, and uplink TTI requests with the signaling for uplink. And the interesting thing about the FAPI protocol is that it expects real-time operation. So new slot indications are sent every slot, and the FAPI needs to receive that slot indication and respond back with the results within a 1 slot window. And if it misses that slot window, we have a FAPI late, and the result is discarded. The slot, nothing is transmitted in that slot. There is a reduction in throughput. This expectation for real time creates the need, led to this definition that we created of the L2 critical path. And the L2 critical path is this basically real-time expectation of the Mac answering to slot indications with the results about grant allocation and PDUs. And the critical path is composed by these 2 main points. The scheduler has to do the process events and schedule the grants. Then the Mac has to assemble, based on the scheduling result, assemble the PDUs that is going to send to the PHY. And then the most critical loop is this back and forth between the Mac and the RLC, where the Mac tells the RLC, okay, the schedule is just scheduled this grant of a certain size. Can you provide me RLC PDUs to fill this grant? And the RLC keeps providing PDUs to the Mac to fill the grants, and then to be then sent over the air. So this is probably the most important aspect about the DU high architecture. Everything is all our designs are centralized on optimizing these critical path. So, talking about optimization, let's move on to the threading architecture. So how basically we can support different deployments and computational platforms. So as I said earlier, we have to support many different deployments. Our threading architecture may vary with the type of deployment you want to do, number of cells, for instance, type of split you want to support, type of computer you're running our code on. Do you have accelerators available? There are many questions. So that affect the threading architecture. So there is not really a one size fits all threading architecture solution for our stack. This is what we discovered early on with supporting ORAN. So it was clear to us that we had to abstract our threading model, so we had to decouple the run domain from the execution policy. So and let me explain what that means. So the run domain is the telecom-specific operations of the DU high, so MAC, RLC, and all those tasks. They need to be unaffected by the type of threading architecture we choose. And the threading architecture is the execution domain, so where the tasks actually run. So if they run in thread pools, in single threads, or in accelerators. And the benefit of this decoupling is that changing the thread model will never require redesigning or recompiling our run logic. So this was our requirement. And to achieve that, we started using this design pattern of the task executors. You might have seen it in our code, spread out through all our code. So what is a task executor? It basically represents a policy of how, when, and where a task dispatched should be executed. It basically, you can think of it as a generalization of the concept of a single thread with a queue of tasks. It can be that, but it can be much more. So, and then to achieve the decoupling, the run domain components, so your layers, telecom layers, will only get access to the abstract task executor interface. And another thing I would like to say about this is that the task executor has to implement two policies: the execute policy and the defer. The execute policy allows the executor, when a task is dispatched to the executor has the permission to run the task in place if he believes it's safe to do so. And the defer policy, where he never has the permission to run the task in place, he always has to enqueue the task in a task queue to be later invoked. And just this figure is just to show how this basically works. So in the entities are the run domain, could be your MAC or RLC, and below is your execution domain. So the threads could be accelerators, could be whatever you have to process. And here is just 3 examples of the run domain, 2 entities of the run domain using different type of executors, but being completely unaware. In the first case, they are using a thread pool. Second, each entity has their own single dedicated thread. Third case, they share a thread. And they are complete. And the run domain entities will never be aware in our stack architecture of what we chose for the bottom half, like for the execution domain. So, and this is, right now at least, how our execution architecture is defined. We don't, as I said, we don't have a single threading architecture. So that's why I put it in quotes. We have more executors, and they can be mapped to threads in the way we deem appropriate. And but here I divide the executors into three categories based on their role. We have the control executor that is responsible for the procedures, like of creation and removal of barriers, for instance, updating the UE configurations, so on. And the control executor has very low priority in terms of kernel priority, and it usually doesn't have huge real-time requirements. Then we have the UE executors that are responsible for encoding and decoding of PDUs. We can have more than one for parallelization. And lastly, we have the cell executors. And we can have more than one depending on the number of cells our DU has. And the cell executors are the ones with the higher mapped to threads with higher priority because they implement the critical path I described earlier. So they implement the scheduling, MAC downlink PDU encoding, and communication with RLC for requesting RLC PDUs. So I wanted to explain how we achieve parallelization in the case, for instance, of the UE executors. So usually, but first let me say one thing. Usually operations on a UE are stateful, at least in the upper layers, not in the PHY. The PHY, most things are stateless, but from L2 to above, things are stateful. So when things are stateful, it's very hard to parallelize. So it's very hard to parallelize tasks that touch the context of the same UE. But we can parallelize across UEs. Like UEs are independent from each other, relatively independent from each other. So we can, for instance, have a parallelization technique like this. So we could, this is a type of static thread dispatch where we can group UEs and based on some policy that we want. It could be like one group is for one cell, another group is for another cell. It's not important, the policy used to group UEs. But each group would then point to a different executor. In this case would be the ones on the left to thread 1, and they would be all running in parallel with the UEs on the second group in thread 2. And as I said before, the tasks of each user would be sequential within the context of the user, but parallel across users. The problem with this threading technique, you may know, is that if one group has more traffic or more tasks to do, and the other doesn't have much work to do, we are wasting one thread. So that's the problem with static dispatch. It would be nice if we, instead of having these dedicated threads for groups of UEs, we could dispatch the tasks to a thread pool, and the thread pool decides based on availability of the threads how to map each task to each thread. But before that, we also have to ensure that tasks for each UE are sequential, because the tasks of UEs are stateful. So the technique we use is this SRAN technique that ensures the sequentiality of tasks for a given UE while the tasks are still running in the thread pool. It's kind of, this might make sometimes, if you're trying to figure out in which thread a certain task of a certain UE is running, it might be hard. And I got this question many times since in this workshop of which thread runs which task. But it's not that simple. The tasks of different components of the L2 can be running in a thread pool, and then there is no fixed thread for those tasks. The task will change, hop between threads depending on the availability of the threads. And this is achieved with this strand technique. And the strand is the way it works is very simple. It receives a task let's say, for user 1. It sees, is the strand currently locked? If the strand is not locked, we can dispatch it right away to the thread pool. If it's not locked, we lock it and then dispatch it to the thread pool. If another task comes and sees that the strand is locked, it enqueues the task internally in the strand and waits for that task. And for unlocking the strand, for this task that we just enqueue, we have to wait for the task that is already running in the thread pool to complete. Once it completes, it's like there is a magical signal back to the strand saying, we finished this task. You can now run the next task that you have pending. And that's how we achieve both sequentiality across within a user and parallelism across users while using thread pools. But I didn't tell the whole story. There is still task prioritization because not all tasks are the same. So we want to prioritize tasks based on their function. So we want to prioritize tasks if they are control tasks like timers and so on, and give different priority to tasks if they are for downlink or uplink. And currently, this is what we use for in our stack. We give the lowest priority to. Sorry, here there is a mistake. We give the lowest priority to the downlink tasks, and the middle priority to the uplink tasks, and the highest priority to the control tasks of a user. Before I finish this section, I would like to show you this little tool we use. Because, as I said, there is no threading architecture. So picking the thread, like unique thread architecture. So you have to pick your thread architecture that matches the deployment you have. But to do that, it's quite hard. So we developed this tool that we call the test mode with the dummy RU that is a way to allow us to see if the threading architecture you chose is able to withstand the traffic that you're trying to run. There is a video here, and I hope it runs. No. No, it's not working, the video. It's OK. I'll try to describe it by using words. So it's just you have to change the configuration and basically activate the dummy RU and activate the test mode configuration. And in the test mode configuration, you can change many parameters. You can say how many, if you want the users to use MIMO, what CQI you want. So we are basically emulating the behavior of UEs and the core and the RU. And we have, since we are emulating, we have to describe a bit how they are going to act, these components that we are emulating. And we define, like for instance, the CQI that UEs are going to report to the scheduler and stuff like that. And it's very simple, the configuration. Once you do that, you run the GNodeB application. It's going to run as if many UEs one or more UEs are attaching. Even if you don't have phones or anything, you can do this run. And if you see lates in the lower layers, like FAPI lates or lates in the PHY, it means that your threading architecture has to be revisited. Maybe you have to dedicate more threads to downlink or to uplink, depending on where you're seeing those lates. So we use this tool a lot to see if the threading architecture we chose matches the use case. So one last note about functional splits. As you may know, in the DU High, we support the split 6 and split 2. Split 2 with the CU, split 6 with the DU low. For split 2, we support these 3 modes, basically. Collocated srsRAN CU, which we call the monolithic G-Node-B app. Remote srsRAN CU, which is a split SRS CU and SRS DU apps, and the third-party CUs. For split 6, we support collocated srsRAN DU low and third-party DU low. And the question is, how do we support so many modes? Again, abstraction and decoupling of the run domain from, in this case, instead of the execution domain, is decoupling of from the communication interfaces used. So here is, by communication interface, I mean operations related with sockets, ASN encoders, and so on. And with these, we achieve what I say here, that layers are completely unaware of which type of split we are currently using. And it's basically this. So we have the layers in our SRS-DU high using gateway abstract classes, and we can have many implementation for the gateways. And here there are examples of files that follow this pattern. But it would be kind of pessimization to always use network-based interfaces for these gateway implementations. Network interfaces have a lot of overhead, as you may know. So we always, for every gateway, implement the fast path solution, which I illustrate here. So whenever we are communicating using direct communication between an srsRAN component and another SRS component, we implement this fast path adapter that bypasses packing and unpacking and network operations and so on. So that's it. Do you have any questions? No.